Hello, everyone, and welcome to part 6 of our Introduction to Risk Assessment course. This is GCU from the University of Minnesota. Today, we will actually conduct a risk assessment for a specific scenario. In this module, you will learn two key skills. First, how to calculate cancer and non-cancer risks using exposure data and risk metrics. This includes using tools like hazard quotients, margin of exposure, and cancer slope factors. Second, you will practice how to interpret those risk estimates, deciding whether the risk is acceptable, and identifying control strategies. These objectives will help you apply risk assessment results to real-world decision-making. In this example, we are focusing on a 3D printing lab that uses photopolymer resins. The specific process of concern is the cleaning and post-processing of printed parts, which can release chemical exposures. The two main chemicals of concern are formaldehyde, a known human carcinogen classified as Group 1, and isopropyl alcohol, or IPA, which is not considered carcinogenic. Your objective in this scenario is to compare the risks posed by these two agents and determine which one presents greater concern. Let's begin with step 1, hazard identification. In this scenario, we're focusing on two chemicals, which are formaldehyde and isopropyl alcohol. Formaldehyde is classified as Group 1 carcinogen by the IARC, which means there is strong evidence that it causes cancer in humans. Specifically, it's been linked to nasal cancers, according to OSHA. On the other hand, IPA is not classified as a carcinogen, but it can still pose risks. It's known to irritate the eyes, skin, and respiratory tract, and at high doses, it may even depress the central nervous system. These hazard identifications are supported by the trusted sources such as IARC, the EPA IRIS database, and OSHA. Understanding these toxicological profiles helps lay the foundation for assessing health risks in the next steps. Step 2 focuses on dose response assessment, where we examine how much of a substance is needed to cause a health effect. Let's start with formaldehyde. For cancer risk, we use a cancer slope factor, which is 0.05 milligrams per kilogram per day based on recent literature. As with most other carcinogens, formaldehyde is treated as a non-threshold carcinogen, meaning that any exposure could pose some level of risk, which is especially important in probabilistic risk assessments. For isopropyl alcohol, we use a different approach. Since it's a non-carcinogen, we apply a reference dose or RFD. The RFD for IPA is 5 milligrams per kilogram per day, as established by EPA. This was derived from a NOAEL, or no observed adverse effect level, of 500 milligrams per kilogram per day in rodent studies. Then, an uncertainty factor of 100 was applied to account for interspecies differences and data limitations. In short, we use different metrics for cancer versus non-cancer effects. The key metrics to remember are, for cancer, inhalation unit risk and lifetime average daily dose, and for non-cancer, RFD and hazard quotient. Now, let's move on to step 3, exposure assessment, where we quantify how much of a substance a person is actually exposed to. We begin with the scenario parameters. These are the inputs we need to calculate those. The concentration of formaldehyde in the air is 0.05 milligrams per cubic meter, and for IPA, it's 80 milligrams per cubic meter. The inhalation rate is 20 cubic meters per day, which reflects the amount of air a person typically breathes in daily. Workers are assumed to be exposed to 250 days per year, and they work for a period of 5 years. We also use an average body weight of 70 kilograms for the worker. For non-cancer risk calculations, we use an averaging time equal to the exposure duration, so 5 years times 365 days, which gives 1,825 days. For cancer risk, the averaging time is based on a 70-year lifetime, or 25,550 days, since cancer effects are typically evaluated over a full lifetime. These parameters will be used to estimate the average daily dose for each chemical, which we will then compare against toxicity benchmarks in the next step. To calculate the exposure, we use standardized equations for average daily dose, or ADD, and lifetime average daily dose, or LADD. The ADD equation is typically used for non-cancer effects, while LADD is used for cancer risk calculations. Both equations start with a similar structure. We multiply the concentration, intake rate, and absorption factor, and then divide by body weight. For ADD, we also multiply by the exposure duration and divide by the averaging time, which reflects the period over which the exposure occurs. For LADD, we additionally account for exposure frequency and divide by a standard lifetime, typically assumed to be 70 years. To support these calculations, we often refer to EPA's Exposure Factors Handbook, which provides standardized default values like inhalation rates and body weights. And finally, exposure values can come from direct reading instruments, personal sampling, or modeling approaches, depending on the data available in the workplace scenario. Let's walk through calculating the average daily dose, ADD, for IPA, as it's a non-carcinogen. We use ADD equation shown here, incorporating our scenario parameters. Plugging these into the formula, we calculate a ADD of approximately 15.65 milligram per kilogram per day. However, in reality, the actual exposure might not occur for the full 8-hour workday. If workers are only exposed for 30 minutes per day, we need to apply a time-weighted adjustment. We adjust the IPA concentration by multiplying by the fraction of time exposed, so 0.5 hours divided by 8 hours, resulting in an adjusted concentration of 5 milligram per cubic meter. Using this adjusted concentration in the ADD equation brings the adjusted ADD down to approximately 0.98 milligram per kilogram per day, which is more realistic for the actual work scenario. This step is important to avoid overestimating exposure and to reflect actual work patterns. Now let's look at the lifetime average daily dose for formaldehyde, which is used to assess cancer risk. We apply LADD formula using the same parameters as before, but we divide by a lifetime average in time, which is 70 years or 25,550 days. We calculate the LADD to be approximately 0.007 milligram per kilogram per day. This value will be used in the next step to estimate the cancer risk associated with formaldehyde exposure in this 3D printing setting. Now that we've calculated the adjusted average daily dose for IPA at 0.98 milligram per kilogram per day, we can move on to characterizing the risk. To do this, we calculate the hazard quotient, or HQ, which is the ratio of the estimated exposure dose to the reference dose. In this case, the RFD for IPA is 5 milligram per kilogram per day. So HQ is calculated as 0.98 divided by 5, which is 0.196. Since HQ is less than 1, this indicates that exposure is within the acceptable range and is not expected to pose a significant risk of non-cancer health effects under these conditions. This step helps determine if any risk management or control actions are necessary. And in this case, for IPA, no immediate action is required based on this exposure level. Now that we've calculated life average daily dose, LADD, for formaldehyde, we can estimate the cancer risk. As shown here, we multiply the LADD 0.0007 milligrams per kilograms per day by the cancer slope factor, which is 0.05. This gives us a final cancer risk of 3.5 times 10 to the minus 5. This means that for every 100,000 people exposed to this level of formaldehyde, about 3 to 4 people might develop cancer over a lifetime. It's important to note that this value falls within EPA's acceptable cancer risk range, which is typically between 1 in a million and 1 in 10,000. So in this case, the estimated cancer risk is considered acceptable under regulatory guidance.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies Program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.